In this video, we're going to look at the conservation of momentum, and we're going to look at kinetic energy too, when we have two objects that collide with each other. And we're going to see, is momentum better to use? Is kinetic energy better to use? Because we already know they're pretty similar to each other in terms of how you calculate them and the things involved. So let's look. Okay, so I have two boxes here that I have set up in Algodo. They're just sitting there right now. I'm going to give this box an initial velocity in the x direction of 1 meter per second. By the way, I made both of these boxes 1 kilogram. I took away friction and air resistance. Let's see what's going to happen when these two boxes hit each other, or when the red box hits the blue box. Okay, it hit the blue box and pushed the blue box to the right, or started the box moving to the right, and the red box moved a little bit to the right as well. This is a pretty common type of thing you might see in real life with two objects hitting each other. This is sort of a scenario that might happen. Of course, aside from the fact that I've taken away friction and stuff like that. There's nothing special really about this collision. Let's look at the momentums involved. Actually, I can just enable momentums here. Okay. Oh, did I take off the speed accidentally? Oh no, it's there. Okay, so let's view the momentums. There we go. So you'll notice the momentum here is listed as 1 Newton second. And remember, it's the speed I made 1 meter per second, and the mass is 1 kilogram. So it makes sense as 1 Newton second, which is the same thing as 1 kilogram meter per second, right? So let's see what happens to the momentum after the collision. Remember, it's starting at 1 Newton second. Ooh, do you see that? I'll zoom in a little bit there. So you'll see after the collision, we have two momentums. Each box has their own momentum. And you'll see that the blue box has a momentum of 0.75 Newton seconds, and the red box is 0.25. What do you notice about those two numbers? Well, they add up to 1, right? They add up to the initial momentum. So in this way, we can say that momentum was conserved in this collision, right? Because the momentum before, which was 1, right, is equal to the momentum after, or the sum of the momentums after. Remember, the blue box to start off with had a momentum of 0. So the initial momentum is 1, right, combined, and then after it's 1 as well, just added up. Is this true of kinetic energy as well? Does all the kinetic energy of this object get turned into, get put in there, or combined? Are they going to add up to the same thing? We can check. And we can do that. Actually, I can right click. We can calculate it by hand, but I can just go here, information. It's telling me that the kinetic energy of this box, the red box, as it's moving at 1 meter per second, is 0.5 joules, which makes sense. 1/2 times mass times v squared. If the mass is 1, the v is 1, it makes sense that it's 0.5. So let's see what happens. And by the way, the blue box will have a kinetic energy of 0, right? Let's see what happens after they hit. Okay, so now the red box is moving slower, so its kinetic energy is going to be less. It's 0.031, so I'm going to put that in my calculator, 0.031. And the kinetic energy of the blue box, where is it? Information, is 0.281. So I'm going to add that to 0.281. I get a total of 0.312 joules. Wait, that doesn't add up to the 0.5 joules we started with. So kinetic energy wasn't conserved. And that's going to be true out of any real-life collision. Kinetic energy won't be conserved. There are special cases that it is, and we'll get to that in a second. But in general, kinetic energy is not conserved. But momentum is. So that's why momentum is actually a much more useful measure when we're dealing with collisions than kinetic energy. The reason why the kinetic energy isn't conserved is because the objects in the simulation have a property called restitution. So both of the restitution of both of these boxes, I made 0.5, which is like the start. It's like a general value. It's the default value. And this refers to like the bounciness of the material. So restitution of 0.5 means it's like 50% bouncy, basically. In real life, everything is a little bit bouncy. So if you think about it, when two objects hit, the total energy before is just kinetic energy. When they hit, some of that kinetic energy actually gets lost. Some of it's lost due to friction and stuff like that, but some of it's lost due to the bounciness of the two things hitting. They're sort of crunching into each other. And when they're crunching into each other, you're actually losing some of that energy due to the collision itself. Every object in real life has some little bit of bounciness, springiness, or restitution. And that's why these types of collisions are very realistic in that way. So what happens if we make them not bouncy though? What happens if I copy these? I'm going to copy this up here. I'm going to copy this. What happens if I get rid of that bounciness? What's going to happen? So what I'm going to do is I'm going to turn the restitution up to 1. So I'm going to make it basically perfectly bouncy. Or like, you can think of it, it's actually, I know it doesn't sound right, but a billiard ball or a pool ball, you know how they're very, very hard, right? When they hit each other, you get that nice clinking, snapping sound when two pool balls hit each other. And you can think of that as like, not much energy is lost because they're sort of perfectly hitting each other. They're not squishing into each other at all, right? So I'm going to make the restitution of both of them 1. So they're perfectly bouncy. And let's see how that compares to the previous case. Let's check. Okay. What did you notice? First of all, we can see the final momentums of the objects now, right? So the top one with the perfect bounciness, the first one, the red box, stopped right where it was. And the blue box continued. And if you know pool, if you've ever played pool, you'll know when you hit a ball with another ball hard enough, one of the balls pretty much stays where it is and the other one continues. And this happens when they're the same mass. Now, that only happens when the bounciness is very high, when there's very high, sort of, as this program calls it, restitution. And that's sort of the similar thing with a Newton's cradle, right? With one thing hitting the other thing. So in this case, we see that all of the momentum got transferred to the second object because of the bounciness. Oh, I realize because of my head you can't see it. There you go. So because of the perfect bounciness. Now in this case, realize kinetic energy was preserved, right? Because we had an object that was moving at 1 meter per second, and now we have another object that's moving at 1 meter per second. So in this case, where the kinetic energy is preserved, that actually has a special name. It's a special type of collision called an elastic collision. So the top case is an elastic collision, and that happens whenever the kinetic energy is preserved in a collision. Now, that's not realistic because in real life, everything has a little bit of bounciness. Everything will behave somewhat like this. And this case is called an inelastic collision. Now, there's one more case we need to look at here. One last type of collision. And that's when it's like you have two objects that are very soft or very squishy. Think of it like two wet sponges colliding with each other. So they have like infinite squishiness. What happens when they hit is they're going to stick together and they're going to move like that. So let's look. I'm going to change the restitution on these two objects to 0. Let's see, material, make the restitution 0. So they're like really squishy essentially. The opposite of a billiard ball, which would be very, very hard, right? Material, make restitution 0. Unfortunately, this app doesn't do this perfectly. So I'm actually going to add one more property. I'm going to add adhesion, which means they're going to squish together. And by squish together, I just mean they're going to stick together. Let's see what happens in this case. Ready, set, go. Okay. So the first two cases, we already know what happens. The first case, the elastic case, the first box stays still. The second box takes all the kinetic energy and all the momentum. In the second case, where it's like halfway inelastic, some of the momentum goes in the first box, some of the momentum goes into the second box, right? So it's still moving forward. In this case where both of those boxes have zero bounciness, they just sort of squish together, both of those objects start moving together by the end. And you'll notice that the momentum is split evenly, and they're only split evenly because they're the same mass. But the thing to realize is that both of these objects are also moving at the same speed at the end, right? They're moving together. So even if they have different masses, they will still be moving at the same speed. And you might say, like, when does that actually happen? Well, the most common sort of example is a car crash, right? If you have two cars that sort of crunch together, their bumpers sort of all crunch together and squish together, and they end up as sort of like one unit that's going to like skid across the ground. And that's happens. And cars are actually designed to take that impact and to crunch the front so it protects the driver as much as possible. But that's a case where this would happen in real life. We call this a perfectly inelastic collision, where they squish together and then end up moving at the same final speed. So these are basically the three main cases of collisions that we're going to deal with. And just to review one more time, the top case is a perfectly elastic collision, where the momentum from one object gets transferred to the other object. It's not always going to work like that. If both objects were moving at speeds to start off with, they would end up with different momentums. But the key in the first one, in the elastic collision, is that the kinetic energy is preserved. The kinetic energy of the system is preserved. So the kinetic energy before the collision and the kinetic energy after the collision, the total kinetic energy, is constant, is the same number. In the second one, in an inelastic collision, just in a general inelastic collision, the kinetic energy is not preserved, but the momentum is. And that's the key. All of these cases, the momentum is conserved. And that's why momentum is so useful to use. And the third case, again, is a perfectly inelastic collision, where the momentum is preserved and the objects end up moving at the same speed at the end. In this course, we're only going to be concerned with this top case, the perfectly elastic collision, so the billiard balls that sort of just bounce off each other perfectly, and the last case, the perfectly inelastic collisions, because those are actually easy to calculate stuff for. The case in the middle, where we have an inelastic collision that's not perfectly inelastic, it's just there's some amount of energy lost due to the collision. Those are much more complicated to analyze mathematically, so we're not going to be concerned with those in this course. Okay? There we go. There's the different cases of collisions that can happen.